Okay, so I thought what we would do today is we'd continue on with our discussion of the Coriolis effect and the Coriolis force acting on a ball that's dropped from rest above the surface of the Earth from some height, maybe we'll call it h. And our goal is to determine how much deflection is there from the Coriolis effect, what direction is it, and basically get a little bit used to using spherical and cylindrical coordinates. Because we kind of need that for a lot of these rotating systems. So let's remember from last time, we wrote down basically the modified version of Newton's second law in a rotating reference frame. And so this A and this R and this V are the acceleration, the position, and the velocity of my object with respect to the rotating system. So these are not inertially measured objects. These are measured with respect to the Earth. And we said that, okay, the first bit is the same as always. This is the net force, which is really inertial forces, so gravity or drag or anything else that's acting. And then we get these three new forces, the centrifugal force, the Coriolis force, and the Euler force. And this dot here is meant to represent a time derivative. Time derivative with respect to, well, I guess that time doesn't depend on the coordinate system here. Let's go ahead and see what we can do by examining a rotating sphere. So we're imagining that we're on the Earth, which has some radius I'll call capital R, and it is rotating in a counterclockwise sense if viewed from above, with some capital omega. And notice that since I need everything to be vectorial here, I'm going to choose this direction to be, well, I'll call it the z-hat direction. Okay, so that's what's going to define my z-axis. It's the rotation axis of the Earth. And this will be the North Pole, that'll be the South Pole. So capital omega is a pretty small number. Well, small compared to what? We'll see what that means later. But we know that the angular velocity of Earth's rotation is 2 pi radians in 24 hours. So in terms of radians per second, it's pretty small. It's like 10 to the minus 3 or 4 or 5, something like that. So now, let's go ahead and see if we can work out some of these cross products. The first thing we're going to note is I'm not going to include the Euler term. We're going to assume that the Earth's rotational velocity is constant. So we're not speeding up or slowing down Earth's rotation. Secondly, we could worry about this centrifugal term. And in fact, maybe it would be worth doing that so that we recognize how to use our various coordinates. So if I'm dealing with a spherically symmetric system, I probably want to use spherical coordinates. So the unit vector in spherical coordinates can be decomposed, if you want, into Cartesian coordinates. What I'm a little bit more interested in doing here is maybe breaking things down in terms of cylindrical coordinates. And the reason for that can kind of become apparent if we think about this in terms of my vector r, the position, is just some distance away from the origin in the radial, and I mean spherical radial coordinate here. And if we work out some of these cross products, let's see what happens. Notice that z-hat is along this axial direction. It's not one of these spherical unit vectors. The spherical coordinates are r, as in a spherical radius, theta hat, which in physics language is measuring down from the North Pole. Unfortunately, physics and mathematics have different conventions for what they call theta and phi. Let's see if I can do a little drawing here. So here is the sphere. This direction we just said is what we're going to call z-hat. Generically speaking, r hat will point radially away from the center. And then I'm going to have s hat. That's not a standard choice of notation, by the way, but it's convenient for a lot of cases. So s hat to me will be the cylindrical radial coordinate. And notice that's directly away from the axis. So it's horizontal. It's radially outwards, but it's cylindrically radial, not spherically radial. And then we'll also have the angle theta coming down like this. So notice that this angle, sometimes called the polar angle here, is the angle theta, and then theta hat is in the direction of increasing theta, so it's measuring south, or at least it's pointing south when you're on the surface. Finally, not shown here, but into the board is the angle phi hat. So that angle is the azimuthal direction in either cylindrical or spherical coordinates. It's the one that's going around following some line of longitude. Sorry, following some line of latitude and changing your longitude. So because we're mixing a cylindrical coordinate unit vector with a spherical unit vector, we are going to need to do some of these cross products ourselves. So let's work this out. Omega cross r, and I'll just do the generic r direction, is going to be omega times r, those are the scalars, and then I need z hat cross r hat. Well, z hat cross r hat is going to be in some kind of phi hat direction, but the thing is, it's not going to be phi hat itself because it's going to depend on this angle theta. And we can kind of see what that is by looking at the geometry a little bit here. Notice that, for example, if theta is equal to 90 degrees, then right-hand rule, z hat cross r hat, which would be directly in the s hat direction, should give me phi hat with no suppression with a sine or a cosine. However, if theta is equal to 0, then actually r hat and z hat are coaxial. They're in the same direction, and the cross product should be 0. Now, in all of these cases, if you wanted to go expand these out in terms of sines and cosines, you could, and you know you're only going to get sines and cosines. So I can just say, well, sine is the one that's 0 when theta is 0, and it's 1 when theta is pi over 2. So this is the right expression for omega cross r hat, or omega cross r, the vectors. We also need omega cross r. Keep on putting unit vectors here. We do have to worry about the parentheses here. We could very easily just take another cross product here, but hey, it's a physics video. Why don't we try looking at the BAC-CAB rule? This is how we can handle these double cross products. So the BAC-CAB rule, as it's sometimes known, says that if I have a cross product, which is A cross B cross C, so the rule tells us that what we're going to do here is I'm going to take B, the vector, and multiply it by the dot product A dot C, and then I'll subtract C, the vector, multiplied by the dot product A dot B. And you can see that this thing does not have any A vector component built into it. It's got to be orthogonal to A after all. And you can go ahead and take the dot product of this with respect to A, and you'll see that these two terms exactly cancel, so that's good. In our particular case, and I'm stating this without proof, by the way, but you could use some index gymnastics or other vector tricks. In our case, the vector A is omega, the vector B is also omega, and the vector C is r. This also kind of shows you why it's not associative. If you try to move these two parentheses over here, you're going to get a different expression that's not equal to this in general. Special cases, maybe. So here we're going to have omega dot r minus r omega dot omega, but that's just omega squared, the magnitude. Omega dot r, well, that's going to have a z hat dot r hat. So if we write this all out in terms of r's and omegas, we'll have r omega squared. That's the general magnitude of everything. My first component here will pick up a dot product between z hat and r hat, but we can see what that's going to be. It's just going to be cosine of theta. And then it'll be in the direction of z hat. So we'll have z hat cosine theta. And then over here, we just have r. So that's just going to be r hat. R hat, based on this little diagram right here, is going to be z hat cosine theta plus s hat sine theta. And if we plug that in right here, we can see that the z hat cosine thetas actually cancel entirely, and we're left with a negative r omega squared sine theta s hat. So that's telling us that the centrifugal force, if you want to call it that, is pointing in the negative s hat direction. In other words, it's radially inwards, but not spherically radially, it's cylindrically radially inwards. So there is a net force, or I guess you can say there's an effective fictitious force pointing towards the axis, not towards the center of the Earth, but towards the axis of rotation. And it does depend on theta and r. However, it does depend on omega squared. And we already said that omega is very small for Earth, at least in terms of the usual parameters we're going to be looking at. Really, when you say something is small, you should say a dimensionless number is less than 1 or much less than 1. And here, we can kind of see that what we're really looking for is omega r and maybe g or v naught. So the speeds that are involved, as well as the acceleration due to gravity, and possibly the radius of Earth. And in our particular case, if you want, what we're looking for here is what? We want r omega squared over g to be small. And it is. Even if you go plug in r, which is fairly large, it's the radius of Earth, omega squared, or omega, is much, much less than the square root of g over r. And that tells us that we really don't have to consider this term. If you really do want to consider this term, you can wrap this up in a kind of effective gravitational field that doesn't point directly radially towards the center of the Earth, but is shifted a little bit north if you're in the northern hemisphere, or a little bit south in the southern hemisphere. Okay, so now that we've kind of written down what this term is, we'll hold it off to the side, but what we're really interested in is this Coriolis force. So let's clear this up. I'll write down this equation at the top with some terms neglected or included, and we'll also go ahead and include the force of gravity. Okay, so here is our result from the centrifugal force. Notice that since this came with a minus sign, the actual effect of the centrifugal force is a minus minus, which is why it's centrifugal, it's pointing outwards. So we do end up with a plus sign here, and maybe I'll go ahead and write this sort of as G naught, meaning the true force of gravity, or the true gravitational field, which is radially inwards. But we can usually lump these together into some kind of effective G, which is approximately radial. Again, we're really banking on this fact that omega squared r over g is very small. Indeed, I got that this is approximately 3.4 times 10 to the minus 3. So I think that's a dimensionless number. So I think it's safe for us to ignore the Coriolis effect, the centrifugal effect when we're calculating out motion in Earth's gravity. Okay, now we've got to figure out this Coriolis term. Okay, well, we could go calculate this cross product in spherical coordinates. Notice that doing so would be quite nasty because r in spherical coordinates looks nice as a vector, r hat. But when you take its derivatives, because r hat depends on theta and phi, the polar and azimuthal angles, you end up with 3 terms in that velocity, and they're going to be really nasty to deal with. So instead, let's do a little change of coordinates here. Let's zoom in to our local patch of Earth, wherever we are on the Earth, and define a little Cartesian frame locally. And what I mean by that is, pretend we're on the surface of Earth, we're at some location, or we're near some location. Remember, this is theta. And by the way, sometimes theta is called the co-latitude, and the reason for that is the actual latitude, this angle, which is usually called lambda, is measured from the equator up. Of course, we're measuring from the pole down, so this is theta. But anyway, let's say we're here, and instead of calling this the z direction now, I'm going to call this the z direction. And just so we don't get z confused with our new sort of normal direction, which previously we've been calling r hat, I'm going to call this k hat. And then what I'm going to do is I'm going to define a northward pointing vector j hat. And notice that that's going to point towards the north. If you're standing on Earth, this vector will point towards the North Pole. Notice that that's going to be, so k hat is r hat, j hat is negative theta hat, because theta hat points down from the pole. And then into the board here is going to be I hat, which points to the east, and that will be phi hat in the usual azimuthal direction. And now it'll be a little easier for us to just write down omega in terms of this new coordinate system that is locally Cartesian, because then the cross product will be a lot simpler. So what we need is omega, and then I have to write this old z hat, which was the direction of omega, in terms of these newfangled coordinates. And the way we're going to do that is recognize that we can write z hat in terms of r hat and theta hat. In fact, it'll be r hat cosine theta minus theta hat sine theta. Why is that? The reason is, if we go back and look here, so this was also r hat, and this direction, how do I want to even write this? I'll write r hat here. This direction was theta hat. You can see that when theta is equal to 0, z hat should align with r hat. They should be equal. So indeed, when cosine of 0 equals 1, I get z hat equals r hat, and there's no piece that's in the theta hat direction. Theta hat's not even really defined at the pole anyway. However, if I'm on the equator and theta is equal to pi over 2, theta hat is actually down. It's in the negative z hat direction. So this term will go away. The sine theta will pick up a 1, but I need a minus, because that'll make sure that theta hat is pointing exactly opposite z hat when theta equals pi over 2. So this is the decomposition of z hat in spherical coordinates. And now we can write r hat very nicely, because it's just going to be what? X dot in the I hat direction, Y dot in the J hat direction, and Z dot in the K hat direction. So writing this out, notice again that r hat is K hat. So we can work this out piece by piece. We'll have an omega. This is the same thing as K hat. K hat cross I hat. Okay, they're on the board. So K hat cross I hat, that's in the J hat direction. So I'll have an X dot cosine theta J hat. It's my first term. K hat cross J hat is in the negative I hat direction. So minus Y dot cosine theta I hat, and K hat cross K hat is 0. For the next piece, I'll have minus theta hat, but don't forget that's just positive J hat. J hat cross I hat is in the negative K hat direction, so I get a minus K hat sine theta, and then of course I kind of sloppy here, the X dot will come along. Remember, this is J hat cross J hat is 0, and then J hat cross K hat is in the positive I hat direction, and we'll pick up a Z dot, and of course the sine theta. Okay, so all of this together will let us write a nice little vector or maybe matrix version of our system here, which has kind of been sneaking off the top here. And it tells us that if we want to write this out as a vector equation, I'm going to write this in my local coordinates as x double dot, y double dot, z double dot. That's the left-hand side. Well, what's this going to be? Notice that this g term, if we ignore the centrifugal piece, which we should because this is small, is just in the negative r hat, aka negative k hat direction. So I'll have a minus g down here. And then in the other directions, notice that this cross product does not have any k hats in it. Or sorry, it has one k hat in it right here. So I guess we'll do k hat first. Don't forget that there's a minus 2 attached to all of this. So the minus 2 will become a plus 2 omega, don't forget the omega outside, x dot sine theta. So we get this extra term attached to my vertical, if you want, acceleration, which depends on the x component of the velocity. Very strange. All right, let's look at the rest. Let's look at the x double dot term. Well, there's no component from gravity to the east, but there is a Coriolis term. Let's look for them. Here's an I hat. Here's another I hat. This one's negative, this one's positive, but there's a minus 2 attached. So I'm going to write this as 2 omega, and then we're going to have two terms. One of them is y dot cosine theta, okay, minus minus, and then the other one is minus z dot sine theta. Curious, the acceleration to the east depends on my northward velocity and my vertical velocity. Weird. And finally, let's look at the y direction. Again, no contribution from gravity towards the north or south, but there are, or I guess there's only one term that is in the j hat direction here. Don't forget the minus 2. So we have minus 2 omega cosine theta x dot. So here is our new system of three equations. The accelerations depend on the velocities in the x, y, and z direction. And now our job is to solve this. So let's bring this up to the top, clear a little space, and then we'll try to think about an approximation method for developing the solution. Okay, so here are the differential equations we have. It's a system. It is a linear system. We could go solve it, but I think the better thing to do here is now to invoke an approximation technique. And the reason for that is we've already decided to neglect the centrifugal component here. So we're really kind of building a solution as a power series in omega. And that means to zeroth, let's say, approximation, let's ignore the three terms that have omegas in them. If the Earth was not rotating, if omega was literally 0, then we would just have z double dot equals negative g, and the others would have 0 acceleration. And we already know how to solve those. Those are the standard kinematics conditions. We would just have, well, we could write it out. I'll start by just writing the z component. And sure enough, if the second derivative is just a negative constant, then we can integrate twice and get our good old-fashioned constant acceleration kinematics equation. The same thing could be true for x and y, except there would be no acceleration. You would just have initial position and some initial velocity components. Let's now look at the dropped ball, just for an example. We'll turn this to projectile motion in a little bit. But if we have a dropped ball, let's say it's dropped from height h. And in that case, we know that x double dot and y double dot both being 0 in this 0th order approximation, we can replace z naught with, we'll call it maybe lowercase h, and we're dropping it from rest. So this initial velocity in the vertical direction will be 0. So here's our 0th order approximation for the height as a function of time. That's with no rotation. And of course, we would just get x equals 0 and y equals 0 following along. We're choosing our coordinates so that everything is kind of lined up above this origin. Okay, now we're going to use this result for these three as a first order approximation into my next order of the equation. So taking this 0th order approximation And maybe I could even put something like little superscripts of 0 on these. Notice that that tells me that the 0th order velocity is just negative gt in the z direction, and of course the 0th order velocity in the other two are still 0. Let's plug those in now and get a new system to first order. So what do we have? We'll have x double dot. Now, y dot is still 0, at least to 0th order, so that term goes away. But z dot is not. The negative will cancel. Don't forget the 2 omega out front. And I'm going to bring the t all the way to the end because everything else is a constant. This depends on your latitude. G is a constant, omega is a constant, t is, of course, time. In the y direction, at least to this approximation, x dot is still 0, so there's still no acceleration towards the north or south. And then this is also still 0, so we have the same result for z double dot. So what's interesting here is this new guy. This is new. And this tells me that the x component of the acceleration, at least in this limit of successive approximations, is linear in time. So I can integrate that twice easily. The first integral will tell me that x dot is going to be, well, integral of t, because a 1/2 t squared cancels the 2 out front. Technically, I would add a plus some initial velocity, but we already said the initial velocity was 0. We're dropping it. And then that tells me one more integration. That the east-west motion of this particle under the Coriolis force deflects it with an interesting cubic power of time, and in such a way that we pick up this factor of omega times g. Okay, so that's kind of interesting. But what I'm really interested in is how far it will be deflected after dropping it from some height. Don't forget we still have this h that's factored in here. Well, notice that to this order, our z equation has not changed. So I can still use this equation even at first order. Maybe I'll go ahead and tell you this is the same thing as the first order approximation also. And I can find out when this equals 0. What time gives me z equals 0? That's when it hits the ground. And notice it's a usual fall time. So t is root 2h over g, which tells me that the amount of deflection is going to be 1/3 omega g sine theta 2h over g cubed, to the 3/2 power. So that's very interesting. If I drop an object from some height, it'll be deflected. Notice this is a positive number. It'll be deflected to the east from where I dropped it. It'll look like it kind of falls to the east. And the amount, well, depends on all these things. It depends on how high you drop it, of course. Higher drop means more deflection. But crucially, it depends on omega. How fast is the Earth turning? It also depends on theta, your co-latitude. So notice that if you're on the North Pole, there is no east. So there's no deflection to the east. Let's just take some numbers, for example. So used to pulling this up. Let's say h is 100 meters. And let's also say that we're on the equator. So if I drop something from 100 meters up at the equator, where theta is pi over 2, that tells me that this eastward deflection is about 2.2 centimeters. Not a very far distance. So it's because omega is relatively small, but we do end up with a measurable deflection. This can actually be measured. And in a future video, we'll go ahead and try looking at this in the context of projectile motion and see what effect that has on, say, the range or deflection. And also what we might do if we start taking this result and plugging it back in again. Then we're going to start picking up a little bit of acceleration in the north-south direction, which will be order omega squared. At any rate, we've gone through a calculation of the Coriolis effect on a dropped ball, sort of the simplest example of a projectile. We've seen how to kind of neglect the centrifugal force, at least to this order in omega, and how we can use this method of successive approximations to get the first order correction to the eastward deflection. QED.